Try building bridge foundations in a gorge nearly 900 feet deep. That's like stacking two 50-story buildings on top of each other. Now imagine pushing steel blocks through thin air blocks that each weigh 90 tons, roughly as heavy as a blue whale. Today we're flying over the Tarn River Valley in southern France. You'll see how 13 years of studies and 3 years of construction turned an almost impossible task into a bridge that, on foggy mornings, appears to float above the clouds. You'll learn why engineers needed a specially formulated asphalt just for this crossing. And by the end, you'll understand why the people who built this thing weren't sure it would actually work until the very last minute. Ready to climb to bird's eye height? Let's go. Every summer, in late August, the same thing happened in the south of France. Thousands of cars carrying tourists heading from Paris to the coast or on towards Spain would grind to a halt at one single point on the map, the small town of Millau, sitting in the Tarn River Valley. The highway narrowed into local roads right through the middle of town, and there was no real way around it. On the worst days, traffic jams stretched for 12 miles. People sat for hours, unable to move. Trucks carrying goods arrived a full day late. Buses full of kids baked in the sun, going nowhere fast. The A75 highway, meant to connect Paris to the south of France, had been under construction since 1975. For 30 years, engineers laid down the road mile by mile, but when they reached Millau, they hit a wall. The Tarn Valley was wide, deep, and lined with steep rock cliffs on both sides. No proven solution existed yet for crossing it. Several bridge concepts had been floated back in the 1980s, but none of them had proven practical. Engineers knew a bridge was the only real answer, but the valley was wide and deep enough that a conventional bridge design wouldn't work. The distance between the two sides was nearly 1.5 miles. The valley floor sat roughly 885 feet below the level of the road. Picture dropping the Eiffel Tower into a pit and still needing several more stories of roadway on top of it. At the time, no highway bridge in the world had ever reached those planned dimensions or combined that height with spans that long. In 1987, the French government officially launched a study, not construction, not even design, just a study to figure out whether this was even possible. Geologists examined the valley floor. Meteorologists measured wind patterns. Mathematicians built models. 13 years went by. Governments changed. Budgets changed. Opinions on whether the bridge was even necessary changed. Opponents said it plainly: too expensive, too complicated, it'll never pay for itself. Supporters shot back every summer. The valley loses money to gridlock, and tourists leave exhausted and frustrated. The argument dragged on, and so did the traffic jams. But during those same years, in two different corners of Europe, two men who hadn't yet met were each working on pieces of a puzzle that would eventually come together into one project. One was a French structural engineer who had already built one of the longest cable-stayed bridges in the world. The other was a British architect whose name was already on buildings in dozens of countries. When the two were finally brought together, they proposed a design that left officials skeptical at first, for all the wrong reasons. Michel Verlogeau, the engineer, had already built the Normandy Bridge, A cable stayed crossing over the mouth of the Seine that was, at its 1995 opening, the second longest cable-stayed bridge in the world. He knew how to calculate cable tension, distribute load, and make steel hold firm at extreme heights. Norman Foster, the architect, brought a different perspective. He didn't just think about how a structure stays up, he thought about how it looks and feels to the people using it. His portfolio included the reconstruction of Berlin's Reichstag and dozens of airports and office complexes around the globe. The Millau Viaduct became a true collaboration between the two. Verloschu's structural engineering paired with Foster's architectural design. Together, they proposed a cable-stayed bridge. That means the roadway doesn't just sit on top of piers, it hangs from steel cables that run down from towers to the deck at an angle. The piers act like masts. They hold the cables, and the cables hold the road. This design allows for very long spans between supports. You don't need a pier every 60 feet. In Millau's case, each of the 6 central spans stretches 1,122 feet, a distance that takes the average pedestrian about 4 minutes to walk. 7 piers, 8 spans. Total length, 8,071 feet. Deck width, 105 feet, with 2 lanes of traffic in each direction. The tallest pier alone reaches 804 feet from the valley floor, and with the mast rising above the roadway, the total structure tops out at 1,125 feet. That's taller than the Eiffel Tower. When these numbers landed on the government's desk, the reaction was cool, to put it mildly. The project was estimated to cost 400 million euros, and there was no public money for it. So officials came up with another plan, a concession. The French government would give a private company the right to build and operate the bridge. That company would fund construction, then collect tolls for 78 years, after which ownership of the bridge would transfer to the state. The company that took on the project was the Eiffel Group, whose history traces back to the historic metalworks of Gustave Eiffel, the same engineering lineage behind Paris's most famous tower. That connection is real, even though Eiffel itself has built thousands of bridges and structures over the years. The Millau Viaduct simply stands as one of its most ambitious. On December 14, 2001, the first stone was laid in the Tarn Valley. 3 years of work lay ahead, and almost immediately, it became clear that the hardest part wasn't the height. It was the valley's challenging terrain, which none of the plans on paper could fully tame. The Tarn River Valley isn't just a pretty postcard backdrop, it's a place with genuinely challenging terrain and weather. Summers here are hot and sunny, but conditions can shift within hours. Clouds gather over the valley, the temperature drops, and powerful winds start sweeping in off the plateau. Officially recorded wind speeds in this area have reached up to 125 mph, fast enough that a person can't stand upright in the open. For the construction crews, that meant one thing. Any workday could be cut short without warning. You can't operate a crane in that kind of wind, it's genuinely dangerous. You can't bolt steel sections together mid-air during heavy gusts either. Work had to stop, again and again. The schedule took a hit, but the engineers had planned for it and built the lost time into the timeline from the start. The second problem was underground. The valley floor wasn't a flat, uniform surface, it was uneven rock. with varying hardness and composition from spot to spot. Geologists spent years drilling test holes and taking samples just to figure out exactly where each pier should sit. Each of the 7 piers ultimately rests on a set of deep foundation shafts, roughly 50 feet deep on average, though the exact depth varied by location depending on the underlying geology. Only after the shafts were bored and the foundations poured could crews start raising the piers themselves. But the real engineering challenge was somewhere else entirely. Building the piers, as demanding as it sounds, was actually the more conventional part of the job. Builders know how to pour concrete from the ground up. The much harder question was, how do you lift 1,100 tons of steel decking roughly 885 feet into the air and assemble it into a single, unified structure up there? No crane available at the time could economically perform a lift like that. You can't lift 90-ton blocks by helicopter. And building scaffolding from the ground at that height would be a project nearly as complex as the bridge itself. Something else was needed, and the engineers found it. The solution was called incremental launching. Simple in concept, but on this scale it becomes something extraordinary. The deck isn't assembled in the air, and it isn't hoisted into place by cranes. It's built on solid ground, at road level, on the riverbank, and then slowly pushed out, horizontally, through open air, until it reaches the opposite side. Picture sliding open a desk drawer, except that drawer weighs roughly 36,000 metric tons and hangs 885 feet above a canyon. The Eiffel Group manufactured 2,200 steel deck segments. Each weighed up to 90 tons, with some sections stretching 72 feet long. Every piece was cut with lasers and plasma cutters to a precision of a fraction of a millimeter. A slight misalignment, and 2 sections simply wouldn't line up at that height. On the ground, that's fixable. 900 feet up, it's a serious problem. The launch happened simultaneously from both the north and south banks. Each pier held hydraulic jacks pushing the deck forward at roughly 150 millimeters per minute, about half an inch every 10 seconds. For a structure that weighs as much as several hundred fully loaded freight trains, that crawl was the only workable pace. Push too fast, and the deck starts to vibrate. Push unevenly, and the load distributes wrong. To keep the deck from sagging as it crossed each open span, crews attached a rigid steel launching nose to the front end, a metal beak that reached forward and found the next pier before the heavy structure arrived. That nose absorbed the impact of any small misalignment. For extra support across the longer spans during the launch, temporary towers were erected, roughly 560 feet tall. Welded together from steel tubing, used only for the duration of the push, and then dismantled afterward. Each of these temporary towers had to bear a load of 7,000 tons. The entire operation was tracked using a combination of GPS satellite positioning, laser surveying, and total station instruments, monitoring the deck's position to a precision of about 1 millimeter. If the deviation exceeded the allowed tolerance, the system halted the jacks automatically, not on an operator's command, but on its own. At that height, the cost of an error was simply too great to leave to human reaction time alone. On May 28, 2004, the two ends of the deck, advancing toward each other from opposite banks, met above the Tarn River. It was the moment the whole team had been waiting more than 2 years for. The connection was officially announced that same day. though the final welding actually took a few more days to complete. Engineers standing in the valley below, looking up, could see only a thin steel ribbon suspended in the sky. One person who worked on the project later said that nobody went home that day. Everyone just stood there and watched. But even with the deck in place, the job wasn't finished. One task remained that almost nobody took seriously at first, and it ended up stretching out for nearly 3 more years. You'd think that, after driving 7 towering piers into the bedrock of a canyon and pushing 36,000 tons of steel through the air, laying asphalt would be the easy part. It turned out to be one of the more unusual engineering challenges of the entire project. Standard asphalt wasn't well suited to this bridge. Here's why. A steel deck behaves differently from a normal concrete road base. Metal expands in heat and contracts in cold, and at nearly 900 feet up, temperature swings between summer and winter, and even between day and night, are more extreme than at ground level. The bridge deck is constantly in slight motion, just millimeters, but constantly. Standard asphalt tends to crack under that kind of repeated movement, which lets water in and can lead to corrosion underneath. Repairing a road at that height is a costly operation, one everyone wanted to minimize. The requirements were demanding. The surface needed to be flexible enough to move along with the metal without cracking, yet firm enough to handle heavy truck traffic without deforming. It also had to drain water well and resist skidding. Developing the right formula ran in parallel with the bridge's construction and took nearly 3 years of testing. Specialists tried different mixtures, adjusted ratios, and ran samples through both lab tests and outdoor trials. The result was a specially developed asphalt mix created specifically for the Millau Viaduct's unique conditions. This detail rarely makes it into the tourist brochures, which tend to focus on height and records. But people who worked on the bridge have said the pavement problem was one of the more demanding parts of the project. Because a flaw wouldn't necessarily show up right away, a surface could look fine for a couple of years before problems developed underneath. There was no way to fully validate the design in advance. The team had to rely on calculations and lab testing, knowing the real test would come only once actual traffic hit the road. More than 20 years after opening, the specially designed pavement has performed exceptionally well, with only routine maintenance required over the years. By the fall of 2004, the bridge was nearly complete. The piers stood. The deck was in place. The cables were tensioned. The road surface was down. One final load test remained. While the crews worked down in the valley, criticism outside never let up.
La vallée, on la sauvera!
Opponents filed complaints, demanded independent reviews, and lobbied officials. Their arguments: the bridge is too heavy for the canyon floor. The ground down there could be unstable and settle over time. A 78-year concession is far too long, and the state will lose control of key infrastructure. The new route bypasses the town of Millau, and local shop owners will lose customers. The money would be better spent elsewhere. That last argument got repeated the loudest. The A75, completed by the viaduct, connected Paris toward the town of Ziers. Critics questioned why such an expensive bridge was needed for a route mostly used during summer vacations. Supporters pointed out that beyond Ziers, the road continues on to Montpellier, the Mediterranean coast, and the Spanish border, a route that carries heavy traffic in summer and serves freight transport year-round, cutting out a detour of hundreds of miles. In the end, the debate was settled by results. The bridge got built. In November 2004, Engineers ran a load test. Several columns of heavy machinery drove onto the deck, together weighing over 900 tons. Sensors across the piers, cables, and deck, installed at hundreds of points and running in real time, tracked every reading. The results matched the calculations. Deflection under load stayed within the predicted range. The bridge behaved essentially as the formulas on paper predicted. The Millau Viaduct officially opened on December 14, 2004, exactly 3 years, to the day after the first stone was laid. French President Jacques Chirac attended the ceremony, walked the bridge on foot, and spoke about France's ability to build things that once seemed impossible. The bridge opened to car traffic 2 days later, on December 16, nearly a month ahead of the planned January 2005 opening date. The Millau Viaduct went on to claim several entries in the Guinness World Records, including tallest bridge pier in the world. The pier, known as P2, rises 84 feet from the valley floor, surpassing the previous record holder, Germany's Kochertal Viaduct, at 594 feet, as well as tallest pier and mass structure in the world, at 1,125 feet total, and highest road deck above ground level anywhere on Earth, at roughly 885 feet. 2 years later, in 2006, the viaduct received the IAP's Outstanding Structure Award from the International Association for Bridge and Structural Engineering. By then, the critics who said the bridge would go unused were already looking at real traffic numbers. The strangest thing to happen after opening, though, had nothing to do with records or awards. It was the fog. Several times a year, especially in fall and winter, the Tarn Valley fills with a thick, low fog that blankets everything below a certain height. On those days, drivers crossing the viaduct see something remarkable. The piers disappear straight down into a white cloud, with no ground and no other vehicles visible below. On foggy mornings, the road appears to float above the clouds, with no visible support between the two sides of the plateau. From below, in the valley, it looks just as striking. Only the tops of the piers and the roadway are visible above a sea of white. That effect turned the viaduct into a tourist destination in its own right. 7 viewing platforms now surround the bridge at different angles and elevations. One offers a view straight up from underneath, showing the full height of a pier and the cables fanning out toward the deck. Another, level with the road itself, lets visitors look straight down the length of the bridge toward the horizon. The town of Millau, which used to suffer through summer gridlock, now welcomes a different kind of visitor, people who come specifically to see the bridge rather than simply passing through. Tourism in the area grew noticeably in the years after opening. As for the bridge itself, it's built for a service life of 120 years. The Eiffel concession runs until December 31, 2079, after which ownership transfers to the French state, though the government retains the right to take over earlier if traffic exceeds forecasted levels. For now, the bridge runs on schedule, carrying somewhere in the range of 3 to 5 million vehicles a year, depending on the year. Sensors on the piers and cables constantly track load, vibration, and movement in real time. Over more than 2 decades of operation, no significant structural issues have been reported, a rare thing for a structure this size. One more detail: the bridge isn't perfectly straight. Viewed from above, it has a gentle curve with a radius of about 12.4 miles. That's intentional. It lets drivers see more of the bridge as they approach and get a clearer sense of where they're headed, making the crossing feel less intimidating than a dead straight span would. Details like that were weighed just as carefully as the load calculations. The Millau Viaduct started out as the answer to a mundane, local problem: clearing a summer traffic jam in the south of France. For 30 years, an unfinished highway ran straight into a valley nobody could cross. 13 years of studies, 3 years of construction, 400 million euros, and thousands of people who climb to bird's-eye height every single day to go to work. The result is a bridge taller than the Eiffel Tower, longer than 20 football fields laid end to end, standing on piers driven deep into solid rock. Engineers developed a specialized asphalt just for this bridge. They built temporary towers as tall as a 50-story building, used them once, and tore them back down. They pushed 36,000 tons of steel through open air at roughly half an inch every 10 seconds. Look at the viaduct from the valley floor on a clear day, and the piers look almost too thin to hold up something this size. But on a foggy day, when the clouds swallow the base of the piers, the bridge really does appear to hang in midair, no ground beneath it, no visible support at all. Just a road stretched between two cliffs at a height where, once, only birds ever flew. If you enjoyed this story, hit like, subscribe to the channel, and tap the bell so you don't miss the next one. There are plenty more stories coming about things that once seemed impossible and got built anyway.